So yeah, Anthony Molinaro. I'm a senior staff engineer at OpenX. And I know you're supposed to traditionally sort of start with a joke, but I couldn't really come up with one, so I just sort of let our marketing guy come up with the title of my talk. So if I can get it to pop up, there it is. So I kind of think it's a sort of silly title, but you know, it's what our marketing guy decided that it should be. So what am I here to talk about? Well, I'm going to talk a little bit about sort of the history of OpenX, what it is, what we do, and sort of how Erlang fits into this picture. And then a little bit about sort of how I conspired to get Erlang used in quite a bit of OpenX. So OpenX actually has a sort of long lineage. It actually started out in 1998 as a PHP ad server called PHP Ads, or maybe it was a script, or who knows. And it sort of went through various name changes over time. Became PHP Ads New, became OpenAds. Eventually, around 2007, it was rebranded as OpenX. And I sort of went and looked at the download. This is sort of the downloadable product. And it's actually installed on quite a few servers, according to one of these online top sites things. And the way it was originally built was pretty much straightforward two-tier app, PHP and MySQL. So I've got a little picture, and hopefully everything comes through here. But what we had is, you know, we had an ad server. We had some way to manage the data. Data was sort of kept in MySQL. And I sort of keep little boxes to keep track of the languages that these components are written in, because a big part of this is, well, how did we get Erlang? So in 2008, the company was incorporated. They hired a CEO who was an employee at Yahoo. He left Yahoo. He lived in Pasadena. The company had been based in Europe, but he didn't really want to move to Europe. So he moved the headquarters to Pasadena and started hiring a lot of sort of ex-Yahoo folks. But at this point, most of the development was still being done in Europe, mostly sort of outsourced there. And they started developing the sort of, the vision for the company changed from like a downloadable product to, hey, let's sort of focus on like enterprise customers, software as a service. We'll run ad servers for them as opposed to them running them themselves. And then in order to make money, we should create a marketplace where, you know, advertisers who maybe don't have a direct relationship with the publishers running this ad server have a place to go and, you know, bid on inventory, you know, bid on eyeballs as they're showing up. So the OpenX, this is called the market, and development began. Since it was still the same people that had been working on the ad server, it was sort of started in PHP. In addition, at this point, Hadoop was introduced because, you know, once you weblogs only get you so far, and there's usually a lot of information you'd like. So there's a protocol called the lightweight event system that is great for sort of logging information, and a bridge was created to sort of dump that data onto Hadoop, and then Hadoop was used for data processing. So we sort of added a few new pieces at this point. Postgres came into the picture because Market was using it a little bit. Hadoop was introduced. And I'm missing a box, but Hadoop is written in Java. So I actually started in 2009, a little bit after the market sort of officially launched. It launched in April, and I started in June. And already in June, sort of the fact that the market was this PHP thing built on top of MySQL and Postgres was sort of already sort of creaking under the traffic that was being driven onto it. A lot of this is because they had made really poor choices, like, well, PHP, but then in addition, they tended to write things to the database with every request. So instead of having sort of an externalized logging system and really using the lightweight event system, they were still just sort of writing data to, you know, Postgres, and then, you know, sometimes 2 or 3 pieces of data for every ad served. So as you can imagine, this doesn't really scale well, and it also sort of required, since it was PHP and Apache, it required a lot of machines to deal with the traffic volumes that we were starting to see. So at this point, there was a couple of people who were sort of Java experts, and they started taking on sort of pulling out certain key pieces and rewriting them in Java. And so the market itself got sort of completely rewritten in Java. And part of the ad server, specifically this kind of ad selection piece, so the engine that goes and determines what ads you're going to see at this point, was also rewritten in Java. And a few decisions were made. The main one was that, like, as we started to kind of tear apart monolithic systems and make much more smaller, interconnected or loosely connected components, we settled on Thrift as an interchange between these because it supported a lot of languages. It provided RPC, which some of the other serialization protocols did not, and so these choices were sort of helped Erlang adoption later on. So where we ended up in 2009 was something like this. I should mention we also introduced kind of NoSQL for our serve time data. So instead of having everything read and write every request to systems, instead we would do things where the management tier would sort of read and write to MySQL, and then we had dumps that came from MySQL and went into Cassandra on some 5-minute interval, and then the serving systems just read directly from Cassandra. And so this eliminated one of the big, essentially like read, all of the reads for the most part on the database. And so the management system was more responsive, being able to just do writes. We would do these dumps, and then the serving system was able to load a lot faster. And then in 2009, this was right after Cassandra had open sourced, and we were basically one of the first people to actually run Cassandra in production, to the point where the developers were actually kind of a little shocked when I mentioned it on the mailing list one time, where I'm like, oh yeah, we're running your stuff in production, and we're seeing these crashes, and they're like, what? You're running it in production? Really? No one's doing that. And I was like, well, we're doing it, so. So by 2010, we sort of had kind of the basics, kinks worked out. The market was humming along in Java, and it was sort of time, once everything stabilizes, it's time to add new features. So the two things that we were looking into, the first off was building a real-time bidding system, which real-time bidding is sort of now sort of the norm in the ad industry, but at that point in time, there was really, Google had just started doing it, and I think we were the second people out there to actually attempt it. And what this is that when you go and view an ad on a web page, if the publisher of that web page hasn't sold that ad directly to an advertiser, then it goes to these sort of marketplaces. And the marketplaces, what they do is usually try to figure out, like, well, does someone care about the user that's looking at this page and want to show an ad? And if so, how much are they willing to pay? And the publisher sort of says, well, I'd like to make this much. And if the amount being paid is more than the amount that the publisher wants for it, then basically you can fill it with that ad. But a lot of these guys don't want to upload all their ads into your market. What they'd like to do is say, well, I have my ads, and I want to wait till the last possible second, preferably right when you're showing this ad. I want to decide whether I want to pay for this or not, whether I want to bid on it or not. So this is where you get real-time bidding. And a real-time bidding system ends up being a request comes in for an ad, and you basically send out a bunch of information to 10, 20, 30 different people and say, here's all the information that I know about who's viewing this ad right now, what page they're viewing it on, their geographic information from IP lookups and things, how much are you willing to bid on them? And some number of them will come back, and then you run an auction based on the bids that come back, and whoever's got if the highest price beats your floor, you can kind of fill it and move on. And all this is happening sort of while the ad is loading in your page. So now you have a sort of better sense of why ads seem so slow. And in a lot of ways, it's, we give people, I think, 120 milliseconds, something like that, to sort of give us an answer for their bid. But this sort of farming out a bunch of requests to a bunch of third-party things is actually a really good use case for Erlang, because it's mostly just sort of keeping track of a bunch of HTTP requests and doing some parsing of the data that goes out and comes back in. So I sort of use this as a first system written in Erlang at OpenX. And I sort of probably started it maybe December 2009. I think we launched it about late January, early February, because it came together very, very quickly. And with a few hiccups in terms of the HTTP client, eventually it got to working great. The other feature that we wanted to add was sort of server-side frequency, especially for the marketplace where you end up having a lot of ads, and people don't want ads being shown all the time, so everyone has a rule saying, hey, if this ad is shown, I want this user to see this ad no more than 5 times in an hour. And what you'd like to do is show them the ad 5 times in an hour, and then after an hour has expired or some fraction of, show it again, because now you can. And at first we kept all this information in cookies, but eventually the cookies get to be a little bit large. So it was decided to sort of move this server side. And around this time, React had just sort of come out, and they published a blog post about React Core. And at first, the developer had been looking into just a pure C database, but I was like, hey, we should look at this React Core thing, because it seems like Erlang would be great for the orchestration layer, and then we can still build the low-level database in C. So this happened. Also, since we were sort of already becoming a little unhappy with Cassandra, I deployed React for some subset of data so we could play around with it. And then we also sort of deployed a monitoring system. And so we finally see some of the my green Erlang color here. The frequency server doesn't come out well on this, but it's kind of, since it's half C, half Erlang, I sort of made it both colors. And again, I missed a box. So the monitoring system at this point was mostly Perl. In 2011, this was the big push to rewrite sort of everything. Like the old PHP code base hadn't been really looked at. A lot of folks had been on the market, and no one really wanted to go near the sort of awful object-oriented PHP code. So we essentially did a clean room rewrite. We basically said, well, what do we want to build? And let's just build it, and let's sort of just not even look at the old stuff, because it's for the most part too ugly to even care about. And since we had a couple successes in Erlang, a couple of the components, we were sort of splitting apart the monolithic ad server into many components, and a couple of them were written in Erlang, a couple written in Java. In addition, our sort of management layer, which had been a pure sort of PHP management app, was split up and sort of made Web 2.0, I guess you'd want to say, where it was web services with sort of an HTML, JavaScript sort of front end. Also, pieces of the monitoring system at this point were rewritten in Erlang with some CouchDB for a back end. So sort of got our architecture to where it looked like this. There's a lot more sort of green popping into the picture. We still had some Java components being written, but sort of more and more Erlang was kind of popping up, and as more people used it, sort of ended up with more. So I'd mentioned we had started to see problems with Cassandra, and most of the problems were actually in the sort of development of Cassandra and the fact that, I don't know, about 3 years ago they made a decision to make a release that was not backward compatible. And that pretty much made it a no-go for us. We couldn't actually upgrade, because our system, the way it was designed or had been built originally, we were tied very closely to Cassandra, which, granted was probably a mistake, but what it meant is that we couldn't really upgrade Cassandra because they provided no way to sort of piecemeal upgrade it. It was like, well, you just shut everything down and just start it back up, and ad serving isn't really a business where you ever get to shut down. So what this prompted me to do was kind of take a look around and see what had sort of developed in the year and a half that we had been running Cassandra. And that's when I came across React and the React Core stuff that had led to other work. But since I had, by this point, also used React a little bit, I said, hey, well, we can use it as a new backend. But what we really need to do is do things right, which is we need to put some layers between us and the data stores that we use. So we developed these data services for our different sort of constituents, the users, the advertisers, and the publishers. And these are sort of thrift services on the front end, and then on the back end, they talk to one or more data sources depending on what they need to do. And this allowed me to sort of migrate first the applications that were talking to the user data service, which was our biggest use of Cassandra, to I first converted them from talking to Cassandra to talking to user data service. Once they were talking to that, I was able to do things like dual write to React and Cassandra in the back end, dual read, and merge the results. And so that allowed sort of a sort of seamless migration from one data system to the other. Also, the API, which had been rewritten in PHP, because there were still a few PHP guys hanging around, it was determined that that was really not scalable. And so they started yet another rewrite on that, which led to sort of a two-tier architecture where they have a front-end sort of Erlang router which routes between different versions. And then the old version, the version 1 is in PHP, and sort of version 2 is in Python. So that got us to sort of the picture of 2012, and it really hasn't changed much since then. The Cassandra box is almost able to be removed from this diagram. as we get closer and closer to getting the various pieces off. But as you can see, there's a lot of green there, so there's a lot of Erlang going on. Well, where did all this get sort of OpenX? Well, it got us to 250 billion monthly ad transactions last year in 2012, which works out to about 4 trillion ad transactions. And since most ad transactions are both a sort of ad request and an impression, looking at about like 8 trillion requests going through our systems. In addition, we had sort of at peak about 12 billion bids per day, which works out to quite a bit. We also have sort of thousands of machines and 5 colos. We're up to about 260 employees, and we booked 150 million plus in revenue in 2012. So, but we're talking about Erlang and the languages. So where did this get us in terms of our components and languages? Well, we ended up with about 9 components on my diagram in Erlang, although we've got a few others that are just not there on the diagram, just because too many boxes. A couple components in Java, although we have a bunch more that I didn't list because they're sort of not part of our serving infrastructure. And then we also had some HTML, JavaScript, some Python. There's still that one lone PHP one. So now I want to talk a little bit about sort of how, because, well, from a company that basically didn't do any Erlang and was a PHP shop to basically having a large amount of Erlang, I think the question that most people have is, well, how did you manage that? Like, did you hire lots of smart Erlang people? What happened? So I'm going to talk a little bit about that, and I kind of think that it sort of was 3 things that sort of contributed to being able to bring Erlang on board. First off was the architecture. Second was sort of tools and automation, and third was evangelism. So shortly before I started, they had kind of decided on some architectural sort of visions of how they wanted to build things based on experience at prior companies and things. The systems were running on Amazon EC2, so it was obviously going to be cloud-based. We're going to run software as a service, but we want to sort of run our software in some sort of cloud infrastructure. So what does this mean? Well, we want to have fairly cheap generic hardware. We want to have a lot of automation. We want to be able to bring up and deploy new servers very quickly. There's something that kind of I brought in, which I call sort of package-oriented development, which really just means like package everything and package it really early. And you need it to be fault tolerant because things tend to just fail all the time in the cloud. So in addition, we wanted it to be service-based. Like instead of having these monolithic servers that sort of do everything, you want to kind of split your problem apart into a lot of different tiers, each tier of which does sort of one thing and is basically given a full box or sizable VM to do what it needs to do. And this allows you to sort of scale each of those components separately. So obviously you need to have kind of pools of components. And then we also knew that we needed to sort of support multiple languages. So that's the sort of early adoption of Thrift as a RPC mechanism has sort of allowed us to know that well, okay, we're using Java right now and PHP, but maybe we want to use something else in the future. So just to kind of skip back to the slide, each of these sort of boxes actually represents a whole sort of cluster of machines. And some of them there may be a few machines, some of them there may be hundreds of machines. It just depends on sort of the component and what it's doing and what its scalability is. And a lot of the challenge is sort of figuring out what the different sizing of these things need to be. But for the most part, the guys that are on the channels on the side, all the guys in the center talk to them through the lightweight event system, which I'll get to in a little bit. And then up and down, most things are Thrift-based. So when requests come in, they'll come in through the gateway, which will send things off to the market or ad selection or RTB via Thrift requests. And they may pull data from one of the data services via Thrift. So there's a lot of things that sort of bounce around in there. So now to skip a little bit to kind of automation and tools. So part of being able to handle the fact that we have a dozen different roles or even more than that is being able to automate the installation of machines with those particular roles on them. So we had a couple of guys who came from Google. They liked this system written at Google called Slack. So it was sort of in place when I got there. This was 2008, I think, when they were deploying it. So I'm not sure if any of the more modern stuff was around, Puppet or Chef or any of these things. But they had a tool they knew, so they used it. And so now we're sort of stuck with it for the most part. And it's a pretty simple tool. It really just uses rsync to just sync a bunch of config and scripts onto a box. It then sort of will run those scripts. It'll run a script, and then it'll sort of take all the files that were downloaded and overlay them on the root file system, and then it'll run another script. And that's about it. But it also provides kind of the idea of roles and sub-roles. So we can have a different role for each of our server types, and then sub-roles for different colos in case we need colo-specific configuration. So this is our sort of workhorse for doing bootstrap and deployment of servers. If we need to sort of start up a new server of a new type, we assign the role to it, boot the machine, it goes out, finds out what it's supposed to be, installs all the software, starts up services, does the configuration, all of that sort of stuff. So another component in tooling is sort of packaging. And I like to I have this thing that I call package-oriented development, which is really about, hey, packaging things, and packaging really for your OS. And the reason you package for your OS and don't use some sort of language-specific packaging thing and things like that is sort of, the barrier to entry is lower when working with an operations group if you hand them a bundle of RPMs for their Red Hat system versus, hey, can you just go install these Ruby gems using something, or can you go install this other stuff which isn't packaged? Because the packaging system lets you sort of have a good sense of everything that's installed on your system. You're able to sort of remove it. So in order to make packaging, so what I like to do is sort of make the entire culture of the development organization about packaging. So this means pushing the responsibility of packaging all the way down to the developers. And developers actually use the package as the main medium of exchange between each other as well as the other parts of the company. So if I need a library that another developer is using, and I need a fix, then they will create a new package for me and put it into a testing repository, and then I can install that package. And if it doesn't quite fix my problem, I can roll back to the previous version that I had a known bug, or I can get them to send me another package. But at every point, sort of the state of what's installed on everyone's system, including the developers, is kind of managed by this system. And in order to do this, we sort of require semantic versioning for everyone and the packages that they create. So some way to know, oh, you're releasing a package, but it's not going to work. It's not backward compatible. So the packaging is a little bit, it can be difficult. If you've ever had to build a spec file or a deb thing, it gets to be a little tedious and whatnot. So that's where a little tool comes in called Framework. And Framework really is a way to basically build packages. But it's also a way to sort of build all of your code. And it also sort of will allow you to have certain organizational requirements on the way code is built and how it's set up. So it sort of has a couple modes. When you're initially creating a new sort of component or package, you use a tool that'll sort of lay out the directory structure for you. It'll lay out the initial build system. And then once that's all done, you have a very common set of commands that pretty much work across any language that Framework has a template for. And these commands allow you to do things like build the code, run any unit tests that are on the code. Certain languages have special things, like the C template allows you to run your code, your unit test through Valgrind. And it enforces that unit tests have to pass before you construct a package. When packages are created, it integrates with your versioning system to basically tag the version of the released software. It sort of builds, along with the package for the runtime, it builds a build time package, which has all the fixed set of dependencies. And really, these are about kind of ensuring that there's some amount of reproducibility, right? If you're going to allow developers to build packages on the VM on their laptop, you want to make sure that if they basically quit tomorrow, you know how to build their package. You're not going to be stuck having to sort of figure out what's going on. And Framework sort of does that for you. If I need to build a particular version of a package, I install the build version for that version. I check out the tag, and my system is basically as close to the state of that system as it was when they built it, and at that point I can build it, make it run tests, do those sorts of things. So another component which I talked about on the architecture side in terms of cloud things was fault tolerance. And fault tolerance in this case is means kind of keeping pools of servers. And once you have a pool of servers, well, now you need a way to sort of spread load across those servers. And at first we looked into various kind of sort of built into the upstream servers pooling systems, but in a lot of ways that was more, we didn't find anything that we liked at first, and so in a lot of cases we didn't really need the features that were there. But we had been using HA proxy kind of in front of everything, but sort of we had this idea like, well, we can actually just use HA proxy to pool all the backend things for one particular service. So instead of having an HA proxy, it sort of inverts it to usually you have an HA proxy, say, on port 80 forwarding to your non-port 80 service. Well, now if you have some other services on another box, and there's like 10 of them, well, you have a local HA proxy, and you have it point to these 10 other boxes. And now your local service just connects to localhost and gets connections through HA proxy. And now it doesn't have to care. And also the HA proxy config can now be managed by your operations team completely separate from your server software. So network topology changes mean usually like an HA proxy reload of a config, which makes it very easy for the operations folks because they don't have to bounce a lot of servers when a machine goes down. Plus, this allowed things like, yes, we know we get automatic sort of failover. We get a little bit of, HA proxy keeps some statistics, so you can keep track of some things. But it does have sort of its drawbacks in that, like, managing the machine lists was done by hand for a long time, and was sort of error-prone and overall like very annoying. Luckily, within the past 3-4 months, we've finally got it sort of integrated with our machine management database, so we can easily just regenerate configs with current lists of machines. And there's sort of one issue that you have with using HA proxy in this mode is that none of your HA proxies know about each other. And if they all have the same machine list and they all are using round robin or least con or any sort of backend thing, they're all going to connect to the first machine in your pool. So under relatively high load, it doesn't matter because very quickly the connections spread out across all your sort of next tier. But under light load, or sometimes if you're doing a restart of the backend services, you can have sort of problems. But that was solved by sort of a nice little hack that basically just randomizes the machine list on each host. So if you have 10 front-end hosts that are talking to 10 back-end hosts, before they all had the same back-end host in the same order on every box. If you restart the back-ends, everyone gets reconnected to that first one. Now the lists are randomized on those front-end hosts. So they hopefully should end up on different machines. So HA proxy is good for quick connections, but sometimes you want to have persistence. And so you can do persistent connections. I mean, you can make a persistent connection and hold on to it, but we actually then needed sort of a pooling mechanism in Erlang. So we wrote something called GenServer Pool. At the moment, we were basically, most sort of connections to things are usually a gen server wrapped around some network, gen TCP or something, and you're usually interacting with the gen server. So being able to kind of just have a pool of these that always stayed connected sounded great. But we already had most things just sort of set up to like spawn up gen servers and do these things. And so looking into the different poolers that existed at the time, which I don't know if there were many, because this was probably have been about 2010. I don't think Poolboy was around or any of these others. But the few that I found all had this, required pretty major changes because they all were check out a connection, check out a resource, do something with it, check it back in. I didn't like a lot of that. So GenServer Pool actually allows you to take any gen server and just pool it with minimal effort. You really just have to change your start link from starting the actual gen server to just calling the gen server pool start link and telling it which gen server to use. And at that point, it'll actually proxy the calls to the gen servers and sort of do auto checkout, auto check-in, and it'll grow and shrink the pool kind of on demand as your traffic increases or decreases. And while this does have the sort of like gen server bottleneck, in most cases you don't really see that unless you get to pretty high loads. So we actually use this not just for kind of loading connections, but like maybe you need to have 8 gen servers to use the 8 cores on your box, you can use gen server pool to kind of spread the load out. We have a similar pool that we use on the Java side, but it's a little less generic. It's specific to Thrift. Another part of the architecture and tooling was these sort of cross-language communication things that I've mentioned a few times. So I mentioned Thrift. We use that for RPC between almost all our components. It supports a lot of languages, which is great. It gives us lots of options if we ever decide to move away from Erlang. We use protobuf in a couple cases to talk to React. Also, our RTB protocol is protobuf, which kind of bucks the modern trend, but we sort of predate the modern sort of OpenRTB stuff. So we'll probably get there eventually. And also the lightweight event system, which is a UDP-based cross-language protocol that's used for logging and monitoring. And so again, just to kind of flash back, LWES is used to kind of communicate with our monitoring and our sort of data collection Hadoop systems. And Thrift is mostly used up and down in our stack, except for a few cases where there's a protobuf. So we've got a lot of components. I sort of laid out a little bit about how we've sort of made deploying these different components and managing these different components a little easier. But the other thing is, well, how do you sort of monitor? How do you keep track of what's up, what's down, whether things are working? So a couple ways. We use Munin for sort of operating system type monitors. And then there's a system called Mondemand, which uses LWES and basically will allow developers to add just small little bits in their code where they say, OK, increment a counter over here, increment a gauge over here, and on the other end they'll have an RRD, and then they can use the built-in graphing components for the RRDs, and it works with sort of all the other RRD-based things that Munin is one of. The other thing, though, that was added that really helps in this kind of big distributed system is what I called tracing. It's somewhat analogous to the Erlang tracing, but a little bit different in that usually what happens is, I had our sort of big stack here, and when a request comes in, it's going to bounce around to 2 or 3 components and look up data and do various other things. So what if something goes wrong? How do you figure out what's going wrong and where? So I've created a way to kind of tag a request as it comes in, and as it flows through the system, it'll sort of trace what's going on. So I had a couple of little screenshots. This is kind of one of our Mondemand Stats dashboards for React, sort of pulling data from the different React nodes and showing request rates and latency. And then sort of an example of what the trace output looks like. So you'll see it kind of comes in to the gateway, goes off to our user server and gets some segmentation information and shows kind of what it got back. And then it makes a request adds to our ad selection engine and passes its various IDs for what it's looking for. And then eventually it'll get some ads back and maybe go and call an impression. And I cut out a bunch of stuff because usually these traces take up pages and pages and pages when they're fully on. But they've actually ended up being sort of extremely useful for our customer support as well as our QA folks in order to figure out what's going on where in the system. Because usually a customer will call in and say, I'm seeing blanks on this page. And so how do you figure that out when they're one customer and we've got thousands of customers and it's all shared software? And so you want to have some way to do it. So usually we reproduce their case and then set up a trace on that reproduction. And then we go through and usually figure out oh, you've got some rule down here in the ad selection thing that's triggering, that's causing it to not do anything further. And so if we go and change this rule, we can fix it. And then sometimes it uncovers bugs and things like that. So that was a little bit about kind of the tools and the architecture and sort of those things. So the last component about how I think we really got Erlang in heavy use is a lot of evangelism. Now the first part of this is it's great, and I was able to do this. If it's possible to fix the game before going in, you can get it to happen. And by fixing the game, I mean look, the architecture choice was hey, use Thrift, use basically this service-based model. These sorts of things allow you to kind of slot in a new language very easily because, well, everything's going to be its own service. And you're using Thrift, which supports 15 languages. So if you happen to want to try out one of those languages and it fits your problem, you can kind of just slot it in. And so that was pretty much kind of, I sort of helped some of that had been set before I got there. Some of it I helped sort of set, and it really helped long term because when it came time to it, it was really just like, well, you need to find a project that really is going to showcase the technology. And I found, well, I've got this RTB bidding system. Erlang seems to fit really well with it. It's just going to be another component, and people are going to talk to it via thrift. So I'm just going to use Erlang, and I think I can do it very quickly. And luckily, we also an organization that's a startup. They're open to new ideas. They said, OK, go for it, try it out. But then the next important bit, which is really the hard bit, is like, well, you need to make sure that it works. If you're going to go out on a limb and basically put your reputation on the line, make sure you're pretty confident about it and make sure that it works. And yeah, you're going to have some setbacks, but you just really have to stick with it and do it. And the other thing that I found really worked was sort of sharing. As I was writing the RTB system, I'm sitting right next to the guy who's still slogging through tons of Java. And my favorite thing to do would be to come up with some neat way to solve some problem that Erlang and functional programming allows you to do in a very compact, elegant way, and then to turn around and be like, hey, check this out, and then sort of walk them through what's happening in your 5-10 lines of code or whatever, and then just watch them get sort of more and more dismayed, and then at the end just be like, man, that would have been 200 lines of Java, and I would have needed 18 builders and this whole thing to do that same thing. And you're like, OK. And the last thing was sort of making it easy for others. And that's kind of how I want to spend the last sort of few minutes, is sort of how I tried to make things easier for the people who were going to come after me using Erlang. So first off was back to framework, which I talked about sort of was a way to sort of lay out packages in a way that they built across everything and that also would end up with an RPM. And luckily, framework had actually been developed using and had an Erlang template already. So I kind of already had that. And the Erlang template itself has sort of ErlRC integration. But around when I was doing a lot of this, rebar was sort of, I guess it came out a little later. So we used FW template Erlang quite a bit. But eventually, rebar was sort of taking over the Erlang world. And framework uses AutoComp and auto tools. So I made a template that would still use the AutoComp auto tools for the packaging layer, and then it would use rebar for the build layer. And then I sort of set it up so that this allowed me to easily just kind of take any third-party Erlang rebar package and turn it into an RPM with just pretty much a single command line. And what this allows me to do is kind of, if there's any third-party dependency that I need, 10 minutes later I've got an RPM. It's in our repository. I now can install it. It integrates with the rest of the system. It just makes it overall very easy. If someone says, hey, I need this package, usually I just package it for them in a few minutes because it's just so fast to do. Or someone needed an updated version of, I think, React Core recently, and it had 8 new dependencies. But it took me, I think, all of a half hour to get everything packaged up and working. So, and also the FW template Erlang rebar is also about the only way, is a much easier way to sort of develop ports and NIFs, just because it does a lot of the compilation and sort of linkage stuff for you. So while most of our packages are still FW template Erlang, a few that need to use NIFs or ports use the rebar version. Sort of the second way that made Erlang a little bit easier for the developers was using some tools also developed sort of with some friends at a previous company. One was ErlRC, and this integrates kind of your package management system with Erlang in such a way that installing an RPM will run through your hot code loading, and if it fails, it'll roll back the RPM. If it succeeds, it'll remove the old RPM. You can sort of upgrade, downgrade, and do a lot of that stuff. And then it also sort of automatically kind of creates sort of boot scripts and things like that. And really, this is because it's sort of meant to be worked on. I'm running a single Erlang node on any box, and I'm installing Erlang applications into that node, where each of those applications is an RPM package, which is a little different than the sort of rebar release style, where it's, hey, I'm going to pull all of my dependencies and put them in this little sandbox. I'd like to get to the point where sort of you can use framework to kind of do both styles, but at the moment it's really tied to ErlRC. And then the other two tools that kind of work with it are ErlStart, which is kind of like starting, stopping things, as well as ErlNode, which integrates with kind of the Red Hat stuff. So all of this was meant to basically make it very easy for someone coming in to get to the point where they have something that's packageable and shareable immediately and not have to worry about a lot of the build system and not have to worry about that. If they're just learning Erlang, they can focus just on the Erlang pieces and not on the messy, crazy deployment pieces. Because a particular new person coming in, like, they're not going to go through the whole process of creating releases and all this unless they're sort of really glutton for punishment and have a lot of time. I sort of wanted to make it so that, okay, you don't know Erlang, but I can teach you, 3 commands to check out, build a package, and you can go and make some bug fixes on this code and release RPMs for it. And with an hour of time, they can actually have a package that's ready for installation on the QA environment or production box. So got a sort of page of links, and the slides will be available online, but a lot of the systems I talked about are open source. A lot of the tools, framework, Slack, GenServer pool, the lightweight event system, Mondemand, and then the Erl RC start and node. So yeah, any questions? Okay, the question was what sort of data are we storing in React? We're in the process of storing all of our data in React, basically. The main data that's sort of currently live and in production in React is our user data. So this is like information about, it's not frequency data, that's a sort of React core outside of it, but we do have other information that has to do with like user retargeting or which segments a user is in. So sort of behavioral type of stuff. A lot of it is not even data that we look at because it's just we give tools to our publishers and then they're able to tag people as in a segment. But we're also looking to move all of our advertiser and publisher data, which is the information about how we, publisher data tends to be like which, ad units do they have on what pages and what rules do they have about matching ads to those ad units. And then advertiser data is for the marketplace, sort of advertisers who are involved in the market. So all of that data is kind of in process of being moved into React for the delivery systems. And then we actually also are using it for the backing store for even our sort of management side of things. So we're in the process of kind of moving off of MySQL, off of Cassandra, and sort of consolidating mostly with React. And actually there's online, I think, my talk from Recon, which goes into detail, is that. So if you're interested, you can check out the Recon talks from last October.
So with this real-time bidding marketplace, I assume you guys take some percentage of like the publisher's bids on each ad as your revenue. And so when money is exchanging hands there, are there any special considerations you have to make sure that no data there is lost or duplicated or other issues with tracking those bids? Like how do you deal with that?
Right, okay. So the answer was in the real-time bidding system, like how does the money work? And do we do anything to make sure it isn't lost? So the short answer is that it all goes through our lightweight event system and then stuck onto Hadoop. And most of what is being looked at are extremely small values. So we actually can sort of, if there's a small amount of loss there, it's not really a big deal. Like we don't do anything special to make sure that that's like, it's not like a banking system or something like that. Most of the time what it is that advertisers in the marketplace have a budget. And the real thing is you don't want to go over budget. So if you lose a little bit, really it comes out of OpenX's end, because the publisher ends up knowing that it happened. And so we do our best to make sure that that doesn't happen, but we haven't sort of made that a requirement just because it's very hard, and you can usually, it's more cost effective to allow a little bit of loss and focus your engineering effort on other systems, like scaling it out to deal with more than it is to sort of deal with like, 1/1000th of a cent that might get lost here and there. So does that answer your question?
Yeah, basically.
Okay. Anyone else? Oh, one more.
Can you, how do you trigger the tracing
So right now it's done with a cookie. So there's a basically sort of place where one of our support people can go. It'll generate a cookie in their browser, and this way they can actually go and trigger it on any of our publishers' sites. So because a publisher's going to, and we can even sort of allow publishers to generate traces, and then we get to look at the trace, but they can generate it. So essentially there's an interface. You go in, you set a cookie, you give it sort of some information about who you are and what you're tracing, and that's the little bit of information that gets sort of tunneled through the system, and it is then used at the end to collate the traces that come from all the different components. So the general bits of the tracing are all open source in the Mondemand project. And so you can, and there's, I think really only like C, Java, and Erlang. There might be a Python one now. But there's a command line tool that you can easily wrap with any other scripting language. And LS supports like a handful more languages, so it wouldn't be difficult to make it work with other languages. But it's definitely like a great thing to have if you're dealing with any sort of like system that has more than a couple servers that your request is going to tunnel through. Being able to just figure out what happened and when and reproduce some problem is great. And I knew it was a winner when basically every single bug request now comes with a trace. So, or every single bug report from QA, and you can sit there and go down and see like, and they basically usually decipher them themselves and say, it looks like the bug is in this component because I expect this to happen and it doesn't. And it oftentimes provides the only way for them to test a really deep in the bowels back-end change is by the trace, values changing and what's being sent from that component. But it does add a bit of overhead to the calls, as you would expect. So they tend to be a little slower. Yeah, well, the cookie is only valid for a short period of time. So if someone gets the cookie and then does a bunch of stuff, like the cookie's only going to live for a few minutes, and then it's going to stop tracing. So, although I think there was one time when somebody mistakenly, turned on tracing for every request instead of just the one, and then we got to watch CouchDB like balloon up and then crash horribly. So, great. Any other questions? Cool. Well, thanks, guys.